welcome to the last session of the day. You guys are workhorses. You stayed the whole time. It's fantastic. We're talking about a different topic besides AI or ML attacks or CI/CD pipelines. We'll talk about quantum. My background is, my name is Mizell. I'm the field CTO of a company called Keyfactor. I'm a software engineer by trade. I worked in big data, compute grids, network engineering, and then I moved into security about 4 years ago. And now I see it from both sides, from the engineering side and from the standard side. And so what's interesting is the quantum realm is heading towards us. So how many of you, huge group, have heard of quantum computers? Okay, so everyone's heard of it. Good, great. So it's interesting. I was at a conference last week in Vegas, and a CISO from the DoD was talking about being prepared for attack vectors that are coming at us. And he was talking about AI kind of hit everyone by storm. Didn't really understand it. It just all of a sudden showed up on the scene, and now we're having issues. And you guys have heard a lot of talks about it. But the good thing is we have some time to prepare for quantum, and quantum's coming. So let's talk a little bit about it. So first and foremost, what is quantum computing? It's interesting, for those of you who watch Big Bang Theory, right? The Sheldon Coopers of the world out there doing theoretical physics, they've been doing experiments on this for years at the subatomic level. And what's interesting is we're familiar with computer bits, very binary, ones and zeros, simple in our minds, ones and zeros. But a qubit, which is a quantum bit, can exist in both states at the same time. It could be a 1 or a 0 at the same time. So it exists as a probability, not an absolute. And particles can be entangled in multiple ways, by putting them close together, by splitting them. And what's interesting is when you entangle particles, they stay connected even at great distances. So what's interesting is if I entangle them both at a position of 1, they'll always be a 1. If I entangle one at a 1 and one at a 0, if I flip them, they'll always be opposite every time. So if I flip this one to a 0, this one's a 1, no matter what distance. It's an interesting paradigm that Albert Einstein called spooky. He's one of the first people to work on this back in his day, which tells you how long the concept has been around. So they've been working on it. What's interesting about it is it just doesn't behave like the laws of physics that we understand today, but yet it actually works. That's the part that's just super interesting. The biggest thing is that quantum its unusual properties allows us to do computations differently than we're ever used to, and at near instantaneous speed. So just to give you a quick example, if I used a traditional computer if you took a maze, and I used a traditional computer to figure out all the paths through the maze to get to the exit, it's going to try every path one at a time until it figures out the way to get out. A quantum computer hits every path at the same time and gives you an instant answer. So it's a very, very different paradigm. So here's the challenge. What if a quantum computer is big enough to be able to threaten cryptographic algorithms? So what happens is all of our cryptography as we know it today is useless. It all can be broken. So if you think about the way keys are done, they use 2 large prime numbers, and you multiply them together. And the idea is, how do I ever get those 2 prime numbers? It'd take brute force computer 1 trillion years to figure it out. So we can outlast that, right? But a quantum computer can do it in minutes, and that's the interesting thing. So RSA, ECC, EDSA, and others will be obsolete, and that affects all of the web browsers of the world. That affects SSH if you're using SSH. That affects any firmware code signing that you do, even Bitcoin, everything that uses PKI. And I should ask, how many people here are familiar with PKI or use PKI? Okay, so we got some PKI folks in the room. Right, so anything and everything that we use PKI for today will become obsolete. It's useless. Now, what's interesting is algorithms that are like AES or a hash algorithm, which is a fixed width, is largely unaffected. Now, there is some new math coming out that they think the weaker algos could be affected, but it's not proven yet. But as it stands today, these seem to be secure, but no one knows, right? Because we're not there yet. So what makes this interesting is this guy, Shor. This is my Sheldon Cooper of the day, theoretical physics. In 1994, he figured out how to use a theoretical quantum computer that didn't exist, how to write the math to break the key. and it's phenomenal. And there's some links to videos at the end of this, and you guys can download the PDF version of this and watch some of these videos. But it's absolutely phenomenal how they figure it out. So if you guys take a prime number, and there's a mathematical algorithm that's used to be able to figure out when you divide it by a lower common number than that starting number, it's a repeatable pattern of remainders, and you're looking for the difference in that pattern. So once I get a remainder of 1, it will repeat at some period of time. So what's that period or that interval? Once I have that number, I can take it into another algorithm, and it'll give me the prime number differentiator. It's absolutely interesting. So the way this algorithm works, the Shor's algorithm, is we put qubits in a superposition of every possible computational value, and then you look for that differentiator. And once you get that period, then I can use a Fourier transfer, pull that data out, and I can go throw it in the next algorithm and get my answer. So it's already being proven against small prime numbers. So the math is there. If you're interested, again, I have some links at the end. You can go actually look at Shor's algorithm. The math is in GitHub. It's crazy. And if you guys are math gurus, I don't think I took enough math in college now, and you look at the math, it's insane, but the math exists. So when do we think a quantum computer can do this? So early predictions said it would take 10 billion qubits to do this problem, to solve it, right? But then as we progress, technology moves fast, and right now, the U.S. government and is putting in like over $5 billion a year into quantum, which that tells you there's a huge investment. China's put in like $15 billion a year. So it's an arms race, right? It's the next arms race. If anyone breaks RSA keys, which is what we traditionally use, they have the keys to the kingdom. So if you guys watched the movie Transformers, and you saw how the Transformer hacked into the mainframe, that's what happened. We're talking real-time cracking, right? So the early predictions, huge. But as we progress in time, technology advances. Now we're looking at roughly 2033-ish is what people are lightly predicting. I could tell you, as fast as things are moving, my guess is it's probably going to be sooner than that. The biggest challenge they're having right now is error correcting. So one of the things that we all take for granted is every time I put a calculation into my laptop, my phone, I do calculation, it's always right? It's always right. The problem with qubits is it's not always right. It's not always proven to be right. And that's where the challenge is they have error correcting problems. So they're trying to solve the error correcting problem and the cooling. Now they've solved a lot of the cooling problems. If you guys are interested again, if you look at the IBM Huron, which is their generation 2, it's actually a beautiful machine, and it's building blocks of adding qubit on top of qubit. And actually one of the videos at the end of this shows the qubit processor. It's just a real small chip like an Intel chip with the qubits in it. They have to keep them at absolute 0. If they get hot, they lose their minds. If some other foreign object comes in, they lose their minds. So it's the instability of it and the like is where the challenge lies. And so that's being worked on, the error correction. And actually, if you watch the Shor's algorithm, they've come up with some error correcting, which is interesting. Again, more math. But as you look at the timeline, it's converging quickly. We are partners with IBM. We actually have a roadshow going on with IBM now where we're actually doing some quantum things, and we'll talk about that in a bit. But this is their roadmap. So here we are in 2024. That Huron is out today. You can see it. You can actually get an IBM developer account if you're interested and play with algos. There's actually another company called D-Wave. Super interesting. You can go out there. They actually have some examples of things you could try, like routes. Remember we talked about looking through a maze to figure out the best route? They actually have some route examples. I actually saw that last week in Vegas at the conference, ISC Squared, if you guys are into that conference. But they actually do route optimization, and it's better than a traditional computer. But you can see this timeline, and you can see the biggest problems. Advances in quantum error correction, and they're actually making more advancements in the arithmetic algorithm from Shor. So those few things come together, we have a problem. And the interesting part is I don't think anyone took quantum computers seriously until Shor's algorithm became mainstay. And people started going, wait a minute, the math is there, the theoretical scientists say it can be true, and then the computer started to get built, and now all of a sudden you have a real problem, right? And then there's real dollars. So it's moving quickly. I still think it's going to come much faster than most people think. So the good news is we have some new algos. So if you guys follow NIST at all, they're the standard body. They've been doing this for a lot of years. All these folks contribute potential algorithms, and it goes through hackathons, and people try to break them using traditional and new methods. And finally, we landed with 3 this year, finally. And so these are available. Now, what's interesting is for those of us who use PKI on a regular basis, it's not going to be the same as what we're used to. So one of the cheats I see with a lot of people is that we set up a new template or cert profile, call it what you like, and we put all the key usages on it, and we'd make it easy, which is bad practice in the first place, but the new algos don't support that. So some are only good for digital signatures. Some are only good for key encryption calculation. So there's a lot of different things coming, so we're going to have to choose differently. The good news is there's more coming. There's more algorithms coming. So Falcon will be out here, I think, end of year, early next year, but I believe there's like 20 more in the pipeline. So I think what we're going to see is an evolution of cryptography over time, because we're trying to get to the best algos, and we need to get ourselves protected sooner rather than later. So the algorithms are coming, but a lot of things need to change, right? So I can't deploy this and everyone use it. So if you guys saw, Google now uses, I think it's MLChem in their browser, and it turned it on and it broke everything because nobody is using any of these algos. And so all of a sudden things were broken. We don't have HSMs that can support it today. So for you guys that are familiar with PKI, you want to generate keys in an HSM, they're protected, your root keys, your issuing CA keys, those types of things. We don't have them, but Thales and the like, these guys are working on it now because the algorithms are finally approved, so they're in that process. Protocols have to shift and change to adjust. If you're familiar with PKCS11 and Microsoft KSP, those have to change. If you guys, not many people here are Y2K, I'm a Y2K guy. We had to go around and update a bunch of machines. Yeah, you guys know what I'm talking about. Well, your OSs have to adjust. They can't take these new algos. Cryptographic library. So we are the behind Bouncy Castle, if you're familiar with Bouncy Castle, but OpenSSL, WolfSSL, they all have to adjust. So anything that uses cryptography has to change to support them. So there's a lot of work to be done. So there's this timeline. This comes from NIST. And so the idea is here we are today. We finally got approval. Everybody feels comfortable with the algorithms. So now, as we mentioned, I need HSM crypto to be able to support it. So you'll see that. I believe we're working closely with Thales and Udamako and others. I believe we're looking at Q1 next year, roughly. So, okay, if we get those, now I can actually have a certificate authority and issue certificates. But now everything else has to support it. So I need it to be supported by, like I said, OSs and webs and devices and those types of things. Things have to support it. So you'll start to see that type of adoption start to happen next year. We're working with a lot of hardware vendors. So your big box vendors, so that they can support it. The backbone of the internet needs to support it, which is kind of our lifeline. And if you guys saw that shitification, right? Maybe that's part of what needs to happen, right? We're gonna get some things fixed. But then organizations have to start adopting. People have to start adopting it. Then we get to critical mass, and then we can start deprecating the old stuff. Now, for those of you guys who are PKI guys, you know that SHA-1, that whole transition was sort of a pain. There's still SHA-1, which is breakable PKI, still out there, right? So that's a problem. So it's gonna be a migration. My guess is we're gonna see a lot of things adjust next year, and then we'll start to see around 2026, 27 companies will start to adopt. Now, if you work with the government or you're part of a government org, you're doing it sooner. There is this concept of harvest now, decrypt later, and it's happening. So our adversaries are collecting data, and they're storing it until they can break the key, and then they can decrypt it. So now there's this concept of, well, when, what data, how long does the data last? What do I have to worry about protecting? So if you think about your social security number, that lasts forever, right? But your credit card numbers roll every so often, and so you got to protect your data now, right? So that's the thing that people are looking at is how do I protect? What do I need to protect now, and move to new algorithms? Now, the advice we give to a lot of customers and friends and family, right? Like, is if you can change and go to a higher encryption strength today with just the current algos, you're better off. Because if you think about trying to break a key, break a 1024 key is a lot easier, leading to less qubits than a 2048, than a 4096. So we start saying maybe we now start looking at, higher levels of encryption depending on the data. And there's some standards out there for that if you guys have to encrypt data, so it's something you might want to pay attention to. So one of the things that's interesting is there's got to be a journey, like we talked about. Hybrid certificates is something that we're working on. It was proposed by some folks on our team. It makes sense. So you'd sign it with a traditional PKI certificate with a traditional algorithm like RSA or ECC, but then there's extended certificate attributes that you can sign with a post-quantum cryptography, and then basically you change, your applications are changing, like your web browser and stuff, where if the person connecting to you can accept the PQ, it'll use that. If not, it'll default back to the RSA. So there's a transition state there, which we're all going to have to go through, right? For those of you guys that don't do PKI, it's everywhere. Everything is connected. Everything that connects across your network has PKI, so it's in a lot of locations. And then, of course, there's other places we'll talk about in a bit. But the other thing that's going to change is the sizes. So if you're working on embedded systems, you might have a problem because there's not a lot of space on a lot of these small systems, TPM chips, those types of things. So if you look at like a traditional RSA and ECC, bless you, you'll see they're smaller, small bytes, no worries. But when you get to the newer ones, I mean, look at the signature size of that DSA, the Sphinx Plus. It's massive, right? And it may not support on a device. Now, traditional laptops and those things will be fine, but it's things that we have to pay attention to as we go. So what do we recommend? So the first thing is to get an inventory of your algorithms. What do you have today? And I heard this great term last week from this CISO. He said that the new term is coming out, which is crypto debt. So much like technology debt or tech debt is crypto debt, how many people know what they're using? I can tell you, I used to write software here. I lived in Atlanta 10 years ago, but actually I was writing a while back, and I worked for a company called McCamish down on Paces Ferry. And I wrote some of my own cryptography back then, which clearly was probably not good. But I was encrypting passwords. Well, imagine what that looks like in an org. If you're a dev, you grab some library to do encryption. Yeah, you don't know what you got.
They were in the news and not such a good that way.
Really?
Was it your code?
Hope not. Wasn't me. I've been out of that business for a long time. But that's the thing. You don't know what you don't have. You don't have a clue. So we need to get an inventory. So there's a lot of scanning tools out there, some new things emerging. How do I get those crypto assets? And then I need to continuously monitor as I change. When we plan for if you're writing new code or building new systems, you have to think about crypto agility. And it's a buzzword we've been using for years, but you have to plan for crypto changeover, right? So we showed you those new algorithms that are out. What if one of those gets broken and you need to change quickly? You can't design a system anymore that's not pluggable. Cryptography has to become pluggable and changeable quickly. Focus on the perimeter first. So if you manage infrastructure, VPNs, and all of your public-facing assets are your first and biggest priorities, right? Because the world has shifted. We used to be in four walls. We're not anymore. We're global. We're cloud. We're everywhere. So like for me, we're mostly remote workers, right? I have VPN on my laptop. Protect that because I'm connected to the office. If I host websites that are public-facing, you need to get in those. And so one of the things is that you'll see the public vendors like the DigiCerts and the Satigos and Entrust and those folks are going to be supporting PQ here very, very soon. And that changeover is going to have to start to happen, right? If you are a software manufacturer, and you guys have heard a ton of supply chain stuff over the last 2 days, a ton. And we talk about a lot of these great tools that'll do the signing and that kind of stuff, and it's great. Well, that's at risk now too, right? Because it could be cracked. And the reason that you care about that is if I get a hold of your key and I can crack it, I can sign on behalf of you. And that's the biggest challenge. You guys have probably seen that happen to Microsoft and a couple other companies where they left their private keys in a GitHub repo. Hey, and now people started taking them and signing them. The other interesting part of that is that the keys were expired, the certificates were expired. But there is a hack, and you could go out and find it. It's called F, and I'm taking the FU out of it, right? It's like F signing, I think is what it's called. And basically, when you do a signing operation, you call that algo, and it'll not look at the certificate expiration date, just bypasses it. So they're signing with Microsoft certificates, and That's malware. Now it shows up on your laptop trusts it, you're installing it. So you have to think about that. So if you sell software, you got to move to PQ quickly, because again, someone will get and sign with your key, and then you're in trouble. And I mentioned this, design for updatability, and roots of trust are going to be changing and adjusting, so you have to think about this stuff. The other thing, this is interesting, and again, I got this at this conference last week. You don't think about all the places cryptography is, but it's in your code too. We talked about this. So your software supply chain needs to be thinking about what crypto's in there. How do I adjust that crypto? How do I test everything, because I'm shifting over? And this is an interesting paradigm. People ask me a bunch, like, do I have to unencrypt my data and re-encrypt it in database? You might. You might be storing data somewhere. So if I change an algo, how do I do that? There's work. It's got to be tested, and you have to be prepared, and you have to monitor and adjust. It's a different world now where we're headed, right? All right, shameless plug. Since I work for Keyfactor, I love to tell people about this. So Bouncy Castle is an open source library. It's 100% crypto PQ ready. It's already released. It works C#, Java, Rust. EJBCA, if you're a PKI person, is our private PKI, second largest PKI used on the planet next to Microsoft, which I don't know what Microsoft is doing. We haven't seen anything from Microsoft. We've talked with them. It doesn't seem like they're doing anything. Post-quantum ready next month. We'll have a release out. It's open source. Grab it, use it. It's there for you. Same thing with signing. Sign server, we can sign using post-quantum algos. And then again, when you think about crypto agility, Keyfactor Command is a certificate lifecycle tool. So that's the shameless plug. Last couple things here. So we have a PQ lab if it's of interest to you. So anybody that likes to get involved with post-quantum, wants to learn about it, wants to try it, wants to issue certs, go for it. It's there for you. There's a link here. Have at it. I also recommend, if you're interested in post-quantum, go to D-Wave, create an account. Go to IBM, create a dev account. They're free. You play around with it, see it. It's always interesting to learn and understand what's going on there. But we're staying right with the top of it, so there's all kinds of information about post-quantum there. So you get a lot of stuff and try it out. I think that's where most people need to be, is just experimental phase. We work with a lot of the big banks, insurance companies, government. How do we get prepared for what's coming? All right. That was quick, man. I made that super quick. I had 8 minutes to go. Those are the algos, or the links I was talking about. They're in the doc you can download. Great. That Shor's algorithm, super interesting. The quantum video is awesome. Takes you through the math, walks you through how it can be broken. Super interesting. Questions? Yes, sir.
You mentioned HSM support will need to come, presumably TPM support
Yep.
as well. Is there any way of modifying TPM hardware that's in existence to kind of support? Probably not.
Not today. It's coming, though. It's coming. So one of the things you want to do is talk with any of your vendors. So if you work with HSMs, talk to the vendors. Where are they at with post-quantum? Talk to all your anybody that you're doing anything that's hardware related. Find out where they're at. But just keep your eye out for it. So like I said, I probably should have put it in here. We have a roadmap slide from Thales that shows where they're at. I should have dropped it in for you guys, but I believe Q1. So we're just talking about a couple months. We'll have HSM support, which means TPMs will be right there probably within another month or two, right in that process. Yep. Yes, sir.
So you said at the beginning, certain algorithms are basically very easily readable with quantum, and certain ones are not, at least you said not yet. So to what degree, when we say post-quantum, is it possible that quantum, to what degree do we expect quantum to evolve to where even what we call PQ today is not always good PQ, or is it just the nature of these things that they should really be pretty immune to the kind of problems that quantum will do?
So it's interesting. It's the type of problems that computer can solve, to your point. So breaking a key that's got two large prime numbers multiplied by each other, a quantum computer can do that when you have enough bits, enough qubits that are stable. It can do it in seconds. It's not even a problem. It's just designed for that type of thing. But the new algos that they're building are using hash-based and lattice-based, much more complex, that a post-quantum computer can't solve, or traditional computers. So that's why it took so long for NIST to approve, because they're trying every possibility. You got all the math experts on the planet, all the theoretical physicists, all these folks seeing, can they break this, can they not, going through that process. So the biggest challenge, like I said, we talk about be prepared for crypto agility, because as we know it today, they can't be. That doesn't mean we know for sure. I think that's the challenge that even NIST will tell you. They feel comfortable, but be prepared. That's why there's more algos coming. Yes, sir. Yes, sir. Yeah.
Okay, yeah. So, first, quick shameless plug.
Sure.
So, I work for the Linux Foundation. We actually have a sister org called the Post-Quantum Cryptography Alliance.
Awesome.
PQCA, which is working on implementing these algorithms for some other libraries.
Great.
But everything you said still applies, because if you're not crypto agile, then you can't change to use these implementations.
100%.
I have a question though, which is, have you given any thought to GIT? Everybody uses it.
Yep.
Everything's based right now on SHA-1
Yes.
hashes, which are already not really a great idea, but it wasn't designed to be crypto-agile in the first place.
Yeah.
Which has made it really challenging to move. Thoughts about that on a post-quantum world?
Well, so it's clearly going to have to adjust, right? No, you don't think so? Well, so once it gets hacked, it's going to have no choice, right? I mean, that's the problem. Because you don't think so? Well, I think. Well, yeah, you can do that, but once you get hacked, I guess the biggest thing is, I think someone said this yesterday in one of the keynotes, was public visibility drives behavior, right? When you hide and you keep it quiet is when things don't change, but when you get publicly abused, so at some point, something's going to have to give, or people will go to a different product. And maybe something that we should, as a company and as a community, is see how we can help. Maybe that's something that I could talk to my team about, because we have a bunch of experts who love open source, and we probably should roll up our sleeves and see what we can do. Yeah. I get this guy back here. Yeah, go ahead.
So now that a lot of these algorithms aren't going to be feasible, at what point are vendors liable for that?
That's a great question. I don't have an answer for that. I don't want to speculate. I think as the era ushers in, as we just talked about, you don't want to be publicly shamed. And then the other thing is that if you're not secure, no one's going to use your tech. So I think you'll see that, like I said, the migration's happening. It's mandated by the government. There's an executive order from the White House to make change. And the first thing they wanted is signing, PQC signing, because they want to protect firmware and assets and software that's delivered across the web. So that's mandated. If you work with the government, you have to. So once that mandate happens, then it goes to the banks and the insurance companies and the telcos, and then it just rolls down. And guess what? Everyone has to follow, or they don't do business. Yeah. Yes, sir. Yeah. For sure. Yes, sir.
Yeah, not to know that today is simulated for quantum computers, or if not, is it possible to create one?
Is it possible to create a quantum computer? To simulate. What do you mean? Like you yourself, or to use one that someone's built?
No, simulated so people can use them.
Yeah, that's what I'm saying. Like D-Wave. If you log, there's a company called D-Wave or IBM. You can log in and get a developer account, and you can try. They actually have try this algo, and you get to see the math, and you can. It's very cool. I do it. It's great stuff. Yeah. Any other questions? Yeah.
Is there any, I can't remember, like, say anything about the advantages of RSA versus ECC as far as the life cycle and post-quantum?
More safe. So once peak, they call it Q day. Once Q day arrives, those algos both are dead. They can be broken. Yeah. The only thing that we recommend is to go to if you need to protect data now and you're worried, is to go to the largest key size you can get, because it elongates the time. Because you think about, if you remember the slide I showed, like the number of qubits it's going to take less qubits to break a 1024 versus a 496, right? So if you have to, go big today, so it buys you more time. But once it happens, you know it's done. Yeah. All right, anything else? Well, hey, I appreciate you guys staying all the way to the end. Thanks for coming. Have a good one. Enjoy.